Hi guys, I'm here to talk to you today about Poiseuille's law. You've probably seen it written, and I had to look up how to pronounce it because I never took French. So, Poiseuille's law. What does Poiseuille's law talk about? You've probably seen this before, might ring some bells. Don't worry, I am going to go through and explain what all of this stuff means. So, LQ over pi r to the fourth. Now, if you remember if this looks familiar, you're probably remembering at this point that it has something to do with fluid flowing through a pipe. Say a pipe that looks a little bit like that, and dot 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 dot. So what do all these things mean? So let's start with the easy stuff. So 8. You know what that means. Pi, that's just pi from geometry, 3.14159, and so on and so on. So, L, the next easiest thing. Notice I'm skipping Q, or I'm skipping mu. So, L. That is the length of the pipe of interest. You know, whatever the pipe is, however long it is, what you can change L there. This is R, it's the radius, and again, this is supposed to be a round cylindrical pipe. Okay, so R, L, pretty straightforward. The things that I haven't talked about so far are mu and Q, and I'll talk about Q first. So Q is the rate of flow of stuff through this pipe. So if you were sitting on this end looking at how much stuff is coming through the pipe, you'd be looking at something like the number of milliliters per second, right? So if you're interested in the units of Q, it is the volume flow, right? So it's volume per unit time. Unit volume per unit time. That's Q. So mu is sort of the newer thing, the harder thing, the more abstract. It's a thing that you probably haven't seen used as many other places. So mu is what we call the viscosity, and viscosity is sort of a measure of how hard it is for something to flow through a pipe. So let's take a couple of substances and talk about their different viscosities. So let's go with liquid H2O. So liquid H2O is going to have a viscosity of somewhere around 0.07. So there's a point there. What we call centipoise. That is the unit of viscosity. If you want to see that in more standard units that you might be a little bit more familiar with. So it's centipascals. This is a pressure times seconds. This is time. Okay, so 0.07 centipoise. This is also a good Scrabble word. Let's compare it to something else that you might be familiar with. So let's take a look at the viscosity of honey. You probably know that honey is pretty viscous, and you see that in the viscosity number. So honey has a viscosity of around 2,000 to 10,000. That depends on, and the units there are also centipoise. And obviously that depends on the temperature. If anybody's ever tried to pour cold honey, warmer honey is obviously easier. So one last substance that I want to talk about, and I think you probably saw this coming, is blood. So blood, typically in sort of a healthy person, has a viscosity of 3 to 4 centipoise. Right? So it's a lot more like water than it is honey. You probably have a sense of that if you've ever had a bloody nose or anything like that. You know that blood flows a lot more like water than it does honey. So how is blood going to flow through a tube? But really, and notice that this isn't specific to blood. This is really any fluid. So you could see a question about oil. If you were a petroleum engineer trying to design a new pipeline, you might use something like this. Or if you're a biomedical engineer and you're designing a new device, you might actually use this equation to figure out how much pressure you need in some system. But we're going to talk a little bit more. We're going to spend most of our time focusing on this biological system, where let's call this a vein. All right. So we've got blood flowing through a vein. Although I guess since I drew it in red, it really should be an artery. Although there are veins that carry oxygenated blood, so I'm not going to change it. All right. So the thing that I want to talk about here is what happens if you change one of these numbers, right? So let's say let's just not mess with R. Let's just keep R the same. One thing I should point out, delta P, if we call this the initial pressure right here and the final pressure over here, delta P equals PF minus PI. Pretty straightforward. All right, so that's this delta P is this delta P. So along the length of this pipe. Okay, so let's say we're going to keep L the same throughout this discussion, but let's say you change Q. So you change the volume flow rate, right? How would you do that? Maybe your heart starts beating a lot faster. So you're just pushing a lot more blood out. So you send Q up. What happens to delta P? If everything else stays the same, what happens to the change in pressure? It goes up, right? This goes up, this goes up. Okay? Sort of same deal here with your viscosity. Viscosity goes up, P goes up. Oh, sorry, let me fix that. So P goes up, right? So mu goes up, delta P goes up. Totally fine. All right, R. What happens with R? Now R is in the denominator, so you probably expect that it's going to do something a little bit different. Let's say that for some reason you've got a clot in here. So remember, this is a vein. You've got a clot. Well, now you're dealing with a new diameter, and let's call this R prime, right? R prime has gone down, so the denominator has gone down, but notice it's to the fourth. So if this radius changes, it's going to have a big effect on P. So if this goes down, this is going to go up a lot more than if this goes up by sort of the same percentage change, right? Okay, so this can be caused by a clot. What I didn't talk about is why might mu change? There are actually a lot of reasons that mu could change. If you have blood and you throw some, say, you got a sick person and they need some saline, right? You give them an IV of saline. What's this going to do to blood? It's going to make it look more like water. So that means it's going to drive the viscosity down. Now let's say for some reason you lose water from the blood. Maybe you're urinating more. What's that going to do to blood? That is going to make its viscosity look a little bit more like honey. So lots of urinating, make it look a little bit more like honey. Still nothing approaching this 10,000, this 2,000 to 10,000, but it can make mu go up. So really the three big things that will change in a biological system are the radius, the viscosity, and the flow rate.